Hello and welcome to my week in astronomy. What I found interesting in the world of astronomy and astrophysics. And this time I want to talk about first light for the Daniel K. Inouye Solar Telescope. I'll show the picture off here, and the telescope actually took this image in December 2019. Of course it takes a while between a telescope taking an image and that being ready to send off to the media. So it's only just really been released to the world, and it seems like a good time to talk about it. So first up, what are we looking at? Well, roughly speaking, this is the solar surface. It's very hot plasma, and to give you a quick idea of what we think is going on here, say you have a mass of plasma underneath the surface and it rises and reaches that surface. As it reaches the surface of the sun, it's going to experience a much lower pressure than it was inside. So a simple bit of thermodynamics, if you've learnt, say, ideal gas or anything like that, you'll know in some way what happens to a lump of something that's free to expand at a lower pressure. It's more complicated than that, but the short is that plasma rising from the interior to the surface should expand and cool. And as the plasma cools, you're then going to get this situation where you have hotter plasma underneath the colder plasma. Again, basic thermodynamics, the heat should rise. So the hot plasma coming from above takes the place of the now cooler plasma again, which falls back down. We have convection. This is a repeated cycle of heat being transferred from somewhere in the star's interior, close to the surface, to the surface. So that's what we think we're seeing here. The brighter areas should be the hotter bits. They are, after all, brighter to our telescope. So in the centre of the blobs you see hot rising plasma, with the stuff that's cooling and falling around these edges of what are called granules. And they're one of a number of interesting solar features that we're trying to get better images of. And that's really a lot of the purpose of this new telescope, to massively increase the quality of our solar observations. It's in Hawaii, in one of the best places in the world for an Earth-based telescope, Mount Haleakala. It's high up, for example, to reduce the effects of the Earth's atmosphere on our images. It has a massive aperture as well, 4 metre collecting. So, to give you an idea, there's something called the resolution of a telescope, the smallest scales you can distinguish between, and it depends on the size of the aperture. To give you a brief idea of what we're talking about, think of a city at night. If you're close up, you can pick out individual street lights, and as you go further and further away, they start to merge together into one big blob of light. And that's an idea of what resolution gives you. It's the minimum angle between two objects where you can tell them apart. So for viewing these tiny details on the surface of the sun, you want that angle to be as small as you can get it. And that means have a larger aperture, because the larger the diameter of the aperture, the lower this angle is. It's also, of course, well kitted out. We've got high quality technology. We've got adaptive optics, which is a way to help correct for atmosphere. We've got the latest tech in terms of receivers and electronics in there. So what else could it do? At the moment, this is fairly near to it, but the next step to improve the telescope is to add multiple devices which are called spectral polarimeters. These are things that have been used in laboratory work similar to. They're devices which work out how much plane polarised light has been rotated upon going through a solution. In the field of space research, we sort of adapt this to something that can give us an idea of the magnetic fields on the surface of the sun or of somewhere else in space. So I suppose after that the big question is why? Why is it useful to humanity to put all this effort into studying the surface of the sun? And I suppose the big goal is space weather. So of course the sun influences weather on Earth, fairly obvious. And we have a reasonable idea of how the sun impacts the Earth's weather in a broad sense, but there's a few areas we could really do with an improvement on. A big example of this is what's called solar flares. Massive increase in brightness in a short flash sends enormous amounts of electromagnetic radiation towards wherever it's aiming at, possibly Earth. Now, especially as we rely more and more on satellites outside any protection from the Earth's atmosphere, this should be ringing alarm bells, serious alarm bells. The electrical damage from one of these catching Earth could be enormous, and therefore the importance to humanity of being able to reliably predict them could be similarly enormous. But you can't just say, I'm going to build a telescope to predict solar flares. because we don't know what causes them really, so we wouldn't know what to do, we wouldn't know what to look for. So all we can really say is, let's say we know they're from the sun somehow, so let's get more detailed data on what is going on in and around the sun, and we'll use that to test and improve our models of solar physics, and maybe something that causes these will come out. We already have some data that suggests that they're correlated with high sunspot activity, but that doesn't mean we can predict them. We can't predict when one will occur very well. Our current standard is pretty much to say, you've got about an hour, lads. Good luck. It would be much better if we had, say, a couple of days in advance notice. So this telescope may be able to shed some light on this, as well as giving us a better understanding of space weather in general. Even less severe examples of space weather may be responsible for smaller problems, such as localised blackouts or damage to spacecraft electronics. One last thing, I'd like to briefly mention the man it's named after, Daniel Inouye. The telescope was originally named the Advanced Technology Solar Telescope, ATST, and was renamed after him in 2013. So from the astronomy side of things, he was a senator for Hawaii and had an enormous influence in the politics of the state over a long period of time. So the turning of Hawaii from a place of great astronomical potential to arguably the greatest ground-based site we've got at the moment, there's very few that could compete with it, that owes a lot to him. On reading around this, however, there's so much more to the guy, and it's good to see his name recorded like this. I'll give a link to his Wikipedia article, and to be honest, have a read. There's a particular section about his involvement in World War II, which is an incredible bit of heroism. So he's assaulting the Gothic line in Italy, a very strong German defensive position, and he's shot in the stomach when assaulting a machine gun nest. After carrying on, he gets hit in the arm by an anti-personnel grenade, which luckily for him didn't explode, but just the force rips his arm off with just like flaps of skin hanging on. So instead of just giving up at that point, he keeps fighting, keeps on going, and then gets shot in the leg and ends up unconscious. My favourite part of the story is that it's reported that on regaining consciousness, what he said to the soldiers now surrounding him is, nobody called off the war, telling them to go back to their positions. That's heroism, that's brilliant. It's good to see what little we can in astronomy to put this guy's name out there. So there you go, an interesting new advance in astronomy, a potentially useful advance for humanity in predicting solar weather, and hopefully a brief description of a rather incredible man. That's all I have for this week. Till next time, goodbye.